All right, welcome. So I made a video and didn't realize that my mic wasn't on. So I'm going to go through this with all the work that I already still have here. Sorry if that makes it a little bit more confusing, but I'll still try to explain it just as thoroughly. So I added these notes here off on the side that you might want to copy down because it's a table that tells us, depending on our degree being odd or even, and if our leading coefficient is positive or negative, it tells us about the end behavior, which I already had highlighted. So what this said is, I'll go back over the graph in green. If our degree is odd, it's going to act just like a cubic function or even a straight line, where if we have an odd function plus an even leading coefficient, it's going to make a graph that kind of looks like a positive sloped line. So it's going to go up, it might have some turning points, and then it's going to keep going up. All right, it's going to have some more curve to it, but that means as we go to the left, we're going to go down. So that's why when we look at our end behavior, as x goes to the left, our y goes down. As we look to the right, we go up. So as we go to the right to positive infinity, our y also goes to positive infinity. So remember how we said our end behavior is always opposite from each other in odd functions. So for the left, it was negative infinity, so on the right it has to be positive because they always are opposite. If our curve has a negative coefficient, it's just going to act like a negative line where we go down as we read left to right. It might have some turning points in here. Might have some more interesting shape in the middle, but on the ends, it's going to look pretty similar to a negative sloped line. So as we go to the left, we go up. So that's why as x goes to negative infinity, our y goes to positive infinity. As we go to the right, we go down. So as x goes to positive infinity, y goes to negative infinity. Again, because it's odd, our end behavior doesn't match. Our even is going to be different. Our end behavior will match. So that means the most classic example of an even function is a parabola. So that means if it's positive, it opens upwards. So as we go to the left, we go up. So as x goes to negative infinity, y approaches positive infinity. On the other side, we said our end behavior matches, and we can see that in our graph. As we go to the right, our curve goes up. So as x goes to positive infinity, our end behavior matches. Y also goes up to positive infinity. If our coefficient, our leading coefficient is negative, that means our parabola is a negative parabola, so it opens up downwards. So as x goes to the left, our y goes down. And as we go to the right, we said our end behavior is going to match. So as x goes to the right, aka x approaches positive infinity, our y is going to approach negative infinity. So that's just some quick notes so we can look at this. If now we look at our work for f, we can kind of start with that. So we're going to start always talking about our degree and leading coefficient. So when we do this, we're going to look at our degree and leading coefficient first. So if we forget, our leading term is the one that has the largest exponent. This is harder to see when we have it factored like our examples in B and C, but for all of our other examples, we had it in standard form, which was no parentheses. And that kind of makes this part of our life easier. So we have our leading term, our degree is the exponent on the leading term, and the leading coefficient is the coefficient on our leading term. So that's how we got 5 and -2 for those. So we said our degree is odd and our leading coefficient is negative. So that's why this one was circled, because that was our first example that we had. We had a odd degree, a negative leading coefficient. So our end behavior, as we go to the left, we will go up. As we go to the right, we will go down. So that's how we got that part. And then remember, our zeros always equals our degree, but it's not just zeros, it's our maximum number of zeros. And then our turning points, all right, our maximum number of turning points will always equal our degree minus 1. And then even though the book didn't ask for it, I was realizing how sloppy that handwriting was, our y-intercept would be equal to this last term here. I didn't see it, so I added it in. I can always add 0 to anything. So y-intercept was 0. All right, so I added some notes up here, which you might want to do. A way to abbreviate degree is DEG, and that is the biggest exponent. Our leading coefficient, which we can just say LC, and that is the coefficient, so the number in front, aka to the left, of the biggest exponent. End behavior, we have that graph, so see that graph, the table. All right, our maximum number of zeros, we can just abbreviate that as zeros, but we need to realize that we have both real and complex zeros, so sometimes these are the ones that we don't see in a graph because complex numbers aren't on our coordinate plane. But that's always going to be equal to our number for our degree. Our turning points, again, our maximum number of turning points, which are our extrema, is always going to be our degree minus 1. So for the rest of the problems, should be kind of fast because we're just using what information we already have in our notes. So we start with this. We look at our equation. I already have it in the box. This is our leading term. 4 times x to the 5th. So our degree is 5 because our exponent is 5. Our leading coefficient is positive 4 because that's what's there. So we can use the fact that our function is odd because that number is odd for our degree, and our leading coefficient is positive because that was a positive 4. And that's how we can get it, that our end behavior, as we go to the left, it will go down. So y goes to negative infinity. As we go to the right, it goes up. So it's just like what a straight line would do that has a positive slope, right? So odd functions behave like a straight line. Zeros, the maximum number of zeros is the same as our degree, so 5. The maximum number of turning points is 4. And then our y-intercept, again, is just this last number. In this case, it was already here, so that's negative 1. If we look at h, all right, all these are in standard form, so it's very little work like what we saw in the factoring during class. We look at our leading term. We notice that in our leading term, our exponent is 4, so that's our degree. Our leading coefficient is negative 1/4. So what we use from that is 4 is an even number. Our leading coefficient is negative, so we can check our table or think about this. For any function that has an even degree, it's going to behave very similar to a parabola. So here it is a negative parabola. So that actually means it'll look like this.
Can I get a cup?
Yeah, it's in the kitchen.
Thanks.
Jimmy, say hello to your whole class because I'm making the video.
Hey, class!
Okay, well that was unnecessary. But our end behavior, as we go to the left in our parabola and on this actual graph, our y will go down. As we go to the right, it'll also go down because in even functions, our end behavior matches. For our zeros, Jamise, zeros, our maximum number of zeros is equal to what other number?
The y-intercept.
No, our degree. Never mind.
I'm sorry.
I will not call on students ever again during the video. The number of turning points, no problem. The number of turning points is our degree minus 1. So that's how we use this 4 to get this 4, and then we do our degree minus 1 for turning points. We could talk about the y-intercept because that's the number all the way at the end, and that was -3. So I just tried to graph it real quick for what I thought it might look like. I'm probably wrong. We can graph that to see. It might not look like that. It might end up looking like a parabola without too many humps in the middle. Our last one, the function that we have to look at, we have this new function. This one's pretty short. We just have x to the 4th plus 2. So because of our leading term, we get 4 as our exponent. Nothing's out as our coefficient, so it's just positive 1. So our degree is even. Our leading coefficient is positive. So we're going to get that parabola type of shape. It might have some humps in it, though, like this. And we'll talk about that in the future. So our end behavior is based on those two things. So as we go to the left, right? As we go to the left, our function goes up. As we go to the right, it's also going to go up. Again, our number of zeros is equal to our degree, the maximum number of zeros, and then the maximum number of turning points is our degree minus 1. So that's how we got 4 and 3. Again, we could look at our function, and we can see that we're plussing 2 at the end, so that's why our y-intercept is 2. So if we go on to the next page, I just wanted to do a little bit more of notes. So I added these here already. I'm going to actually erase it and redo it so I remember what I was talking about. It's having you actually look at the function and figure out some more information about it, but we can kind of assume some of this information. For all of our power functions, or polynomials, and you'll hear that word sometimes, and they describe different but similar type of functions, the domain is always all real, but the range is what kind of is different. If the function is odd, our range looks like this, right? Our y values, so our y values for a function that looks like this, it's going to be all real. But for even, this is the one that takes a little bit more work because we have parabolas, we have degree 4 functions, we could have a degree, what would that be? 1, 2, 3, 4, 5, 5. So 5 turning points, which means degree 6 at least. They all have this kind of weird thing where we have y, here it might be like y is greater than -1, here it might be y is less than 3, here might be y is less than 10. Our range is limited, so we have to be careful with our range. The zeros is what was going to get a bit funky, and we've kind of started talking about that. We can have real zeros versus complex zeros, and we don't see these on a graph. All right. Our relative maximums and relative minimum points, again, we have ones that we see and don't have. So even though it says we could have a max of 4 turning points, we might end up only seeing 2 extrema or something like that. So sometimes these get hidden, and we can talk about why that is in the future. But for now, just know that our relative extrema won't always equal the number of turning points that we think we'll have. And then intervals of increasing and decreasing, those are related to our extrema, and we talked about that in the last section. Lastly, number 5, what is the relationship between double roots of a polynomial and the relative maximum and minimum value? So this double root, we were talking about when we were talking about multiplicity in class. I feel like I spelled that wrong. Multiplicity. Yeah, definitely spelled that wrong. So we can abbreviate that ULT. Our multiplicity of a function is if it's in factored form, we see an exponent up here. So we could have something that looks crazy like this, right? And all of these factors have multiplicities. So when it's a double root, that means our multiplicity is equal to 2. So these right here would be double roots. And something very special happens there is even though we said roots are our x-intercepts, and Tyler was getting this a little bit in class, he said, I didn't think turning points could be an x-intercept. Well, when we have a multiplicity of 2 or 4 or 6 or any even number, it'll go up to the x-axis and what I call it kisses it. So it might come down like this, and then, so that would be, if we actually try to graph this function, that would be at -5, right? So that would be this one. So we have x-intercept at -5, but because the multiplicity is 2, kind of just kisses it. And then it goes all the way, it goes to +2, where it again comes back and kind of just kisses it because this is a double root, so that's at 2. And then at 3, even though it has an exponent of 3, because it's odd, it's not going to kiss it, it'll actually go through it. All right, so we have this degree function. We have 2 plus 3 plus 2. So we have this degree, which is 7, and we said it has a maximum of turning points of 6 and a maximum number of zeros of 7. But here we see only 1, 2, 3 zeros in actuality, right? And our turning points would have to be 1, 2, 3, 4. So we don't actually get the full number, and we can kind of see that in factored form, where since we have these multiplicities, because we have these exponents on our factors, that's why our zeros isn't the full number. So we have 3 different factors here. So that's why we have 3 different zeros, all right? So we'll talk about that a little bit more once we're all back in the class. So for the check your understanding, which we did not cover in class, we can talk about this now. But we can list the important information from the graph, approximate any values. I don't know how you would ever approximate to 3 decimal places. We can approximate it to 1 decimal place. I have no idea what the book was thinking. So with this, important values, we always start with domain and range. Here they're all reals because it's an odd function. And then we can start talking about our x and y intercepts. So this is where we're going to have to start approximating, right? X-intercepts is where it crosses the x-axis. So we have that one, which looks like it is, looks like our scale is every 2. So our first x-intercept would be -3. That one looks halfway to -1, so -0.5. This one is a little bit more than halfway between 1 and 2, so maybe 1.6. And then our y-intercept, again, we're going by 2s, and that looks like it hits exactly halfway between -2 and -3, so -2.5. So those are the intercepts. We also call these our zeros, or our roots. The next thing we have to talk about was our extrema, which we said here and here, right? Because that's where the graph turns around, right? So these are also our turning points, right? So these are the same thing. So our extrema and turning points, we have a relative max, and we know it's relative because this part goes higher than that hump. So we have a relative max. We can either say at x equals, and we can follow that down to -2, or we can actually say the point, which would be -2, and then it goes all the way up to 5. And then we also have a relative min at x equals, and this one's going to be an approximation. So maybe x equals 1.6. I'm sorry, 0.6. Or a coordinate point of 0.6 and just a little bit more negative than -4. So maybe -4.3. So that would be our extrema or our turning points. We can also maybe claim our degree at least here, and we can actually go backwards because we have 2 turning points. So that means our degree could be 1 more than that. And what else did we talk about? We talked about M behavior and our leading coefficient. So we can look at this graph, and because it starts down here and ends up here, right? We can say that this graph has a positive leading coefficient. We can't really figure out what number it'll be, but we can say it's a positive number. And then for our M behavior, we know our degree is odd and our leading coefficient is positive. So that means as x goes to negative infinity, y goes to negative infinity. As x goes to positive infinity, y goes to positive infinity. So a little bit more, but the bell just rang for passing period, so I need to go out in the hall. But we kind of talked about this already. But hopefully this is enough notes for everybody. Good luck in class. Again, you're going to be looking at your homework. I'll have the sub pass it out. You'll go over it by yourself online, and then the sub should also pass out a worksheet for you to do. Do it honestly. Do it within your group. And then I will put it into the quiz category at not a full quiz points, but I still want to get into the routine of us taking a quiz every Friday, turning in homeworks, turning in do nows, and taking this class as serious as we ought to.